everyone. Thank you for coming. We are very honored to have Professor Jensen from NUS to give us this talk on computational design. So feel free to ask him questions after the talk, so that you have an idea of what to do for your speech competition. Okay.
Thank you. All right. So I think this in the virtual world. So there's some of you here, but I think this is all going to be recorded. So I'm assuming there's going to be thousands of people watching this later. So we are talking to true audiences here. All right. So today I'm going to talk about the tool that we've been developing through research and teaching called, and the tool's called Mobius Modeler, and it's a web application in the Chrome web browser, and it's an open source tool that we've been developing for a while. And so today what I'll do is I'll first spend 30 to 40 minutes with PowerPoint slides, going through a bit of background concepts behind the tool, and then spend 30 to 40 minutes on the hands-on kind of stuff. And so the hands-on stuff, I'm not really expecting you to follow. It's more that you can actually see how the tool works, and I'll go through some models and explain some things. So the tool is, you can go, I mean, if you do have your laptop here, you can go to this web address, and then you can use the tool. It's free. You just go there and you can use it. So the tool is basically it is a kind of programming environment. It's basically like what in programming you would call an IDE, which is an integrated development environment to write code, like a kind of coding tool. But the difference with this tool is that the coding is done more or less visually. Mostly we're trying to make it a kind of visual coding approach rather than having to write lots and lots of text, because visual coding is going to make it easier for you to pick up coding. The way that we've created this language and everything is very similar to Python in terms of a computer language. And so when you learn this tool, you're kind of learning coding that's very similar to Python. So once you've learned this tool, it's quite easy to then switch over to textual programming, or at least it will be easier to switch over to textual programming. And let's say in Grasshopper, where you have this, does everybody know what Grasshopper is? Yes. Let's just check. Some of you don't know. So in Grasshopper, you have a script node where you can just write textual scripts. So the idea of Mobius is that you can do lots of stuff in Mobius, but it's also a sort of gentle learning curve into other kind of textual programming. So once you've learned Mobius, you can either just keep using Mobius, or if you want to do more advanced stuff, you can then progress onto the textual part. So there's kind of a few things which are sort of novel in Mobius. I mean, the tool itself is a new tool, but what the key differences between Mobius and other existing tools are these three key points. Firstly, there's this visual programming language that we've developed that is a bit different from Grasshopper and those kinds of tools. And I'll talk a bit about that. I'll talk about all these three. There's this file format where we're trying to integrate geospatial information, and geospatial means GIS, so kind of data from GIS data, with the kind of parametric modeling environment. So this second one is a new kind of file format that the tool uses. And then the third one is the ability to publish your models. So this means that if you make a parametric model, you can then push it onto the internet, and you can have a website where people can move the sliders and click execute, and it generates a new model. So it's like a parametric model that is available to other people to play with on the internet. And so that's also a kind of third kind of novelty. All right, and then as I go through this stuff, you can stop me at any time and ask questions. All right, so first, I mean, maybe I have 4 or 5 slides and a bit of background. So why is it really, you know, why computational design? And why, you know, not just do stuff in SketchUp? It's also difficult, right? So I think the why reason is important to understand that there is a kind of broader, there's a bunch of things that we can achieve in the long term and a bunch of things that we have achieved now. The answer to the why question is maybe more when you're looking long term. So the first thing to talk about is perhaps the global challenges that we're all facing in terms of design. So the IPCC is the International Panel on Climate Change, and it's an important multinational organization that does research and writes reports about climate change. And so the latest report came out just a few months ago called SR15, and it's about keeping the temperature down to 1.5 degrees centigrade. So the report, and basically these graphs are kind of showing, like, you know, we're going up, and you either try and level off, or probably we won't be able to the first one, so we're going to overshoot, and then we try and bring it back down again. But the report is really about the difference between, if we keep it to 1.5 degrees, what will happen, and if we go to 2 degrees, what will happen. And so the report is written in a very kind of, we can save the world positive way, but when you read between the lines, it's a very depressing report, because it's not very good news in the report. So for example, if we go to 2 degrees C, then all the coral reefs in the world will die by 2050. If we go to 1.5 degrees C, then only 90% of them will die. So we'll still have 10% left if we can keep it to 1.5 degrees C. And that is just one example of hundreds of things where you say, okay, if 0.5 degree C doesn't seem so big, but it's like everything is so important to try and make this happen. But the reality is that to make this happen is that the building emissions would, let's say, to keep it to 1.5 degrees C, the building emissions would need to be reduced by 80 to 90%, which means, so in the NUS now, I'm sure you've heard about the new building at the Architecture Department, the net zero energy building. Everybody's heard of it, yeah? All been there. So this is great, right? So it's actually 100%, not 80 to 90, but 100% reduction. The only problem is that that's only one building, right? And so we have to do this for every building in the whole world in the next 30 years. So imagine every building in SP, imagine all the old buildings, imagine all the buildings, bad insulation and old air conditioning, whatever. So in the next 30 years, we have to make them all 80 to 90% more efficient. So it's almost, you know, well, I don't know what to call it, really. It's scary in terms of how we're going to achieve this. And so I think one of the things that, one of the aims of computational design, or at least one of the aims that I think, rather than just making strange-looking forms that are expensive to build, well, computational design seems to be about making very flamboyant architecture, but I think there are other goals that we can focus on. And so one of the goals, I think, is to try and at least contribute to some kind of solution for this better future. So computational design is not going to be the answer, and it's not going to solve climate change, it's not going to solve all these problems, but it may be one of the tools in your toolkit that can help you. Because if you're going to change all the buildings to be 80 to 90% more efficient, just designing like you usually do, sketching and coming up with some ideas and running a simulation in the final moment before you hand over to the client, that's not going to work. So you're going to have some other kinds of process. So this was an example from a few years ago where we took an estate and said, okay, we need to get so many thousand flats in there, and the flats need to be, some percentage need to be 5-bedroom, and some need to be 3-bedroom, 2-bedroom, and some need to be on the ground floor and all this. And we put all those constraints into the system, and then it generates lots and lots of designs. So it generated about 10,000 different designs. And each design was then simulated and tested, and so that we could find designs where the view area of your window was good, and you weren't getting too much noise from the roads, and you were not getting too much solar radiation, and the profit for the developer in terms of the profit that they can make on development is still high enough to make the project feasible. So looking at a whole bunch of constraints and generating lots of designs. I think there's, I took out some slides here to picking the wrong thing. So really this is a selection of designs where the buildings have been rotated and changed, and the heights have changed, and the positions of the water features in the middle have changed, to try and get a configuration of buildings that maximizes the buildings with all the good performance. So this is research we did a few years ago. We've done a bunch of projects like this where we're optimizing complex kind of systems. But the reality is that this is not, sorry, I keep pressing the wrong button. This is not accessible to most people. Most architects will look at that kind of process and say, well, it's great, but it's all these things. Too demanding to build, and too demanding to comprehend, and too demanding to modify, too demanding to manage, and too demanding to execute. It's just all too complicated. I can't do it. I don't have time. You get this kind of spaghetti code where everything is connected to everything, and it's very difficult. So only 5% of users can really do this kind of stuff. And if we're going to change the whole planet in the next 30 years, then 5% is not enough. We have to get tools that everybody can use. And so the tools have to get easier, and they have to get more accessible, and that kind of thing. So, and it's really a kind of different point of view from the software industry. The software industry has been developing tools. They never seem to get easier to use. They always seem to get more difficult. So SketchUp was one example of easier. And then the software industry is mainly focused on making money, not changing the world. So it's a slightly different focus. So here we're trying to say, okay, how can we make tools that are cheaper or free at least, even free if they can't be cheaper, so that it becomes much more accessible and everyone can use it. So this is a little diagram of the number of architects in the world, which was estimated to be about 3 or 4 million architects in the world. Italy has the most. Italy just has tons of architects per head of the population. So for every 414 people in Italy, there's one architect. I don't know what they do, but anyway. They probably go abroad and design, I don't know. And then China has the least architects per head of population. So if you're in China, you have a lot of work. So, but overall, it adds up to 3 or 4 million architects. If you then take all the urban designers and all the other people designing our planet, you may say that there's 10 million people designing the planet over the next 30 years. So that gives each designer 2.5 minutes of construction. So if you think everything's built over the whole world, down and divided, you get 2.5 minutes of that construction. So, but what are they going to do in those 2.5 minutes? What are they going to build? They're going to build stuff mostly, using tools that don't have a lot of advanced capability. So that is why, the Mobius modeler and the Mobius ecosystem was started, and why we were trying to develop these tools. So the idea is to try and make a computational design environment that is very accessible to everyone. That doesn't mean that it's going to be really, really easy. It's still going to be difficult, but we're going to try and make it as accessible as possible. Computational design is partly programming, and programming is a complicated thing, especially if you're not trained computer scientist. So the programming part is always going to be a challenging learning curve. But but we now need to try and make it as easy as possible. But what we want to make sure is that in making it easy, we don't dumb it down. So in trying to make it easy without dumbing it down so that it's no longer powerful. We're going to try and make it easy but still keep all the power behind it. So Mobius Modeler, it's free and it's online, and the code is executed in your browser, so there's nothing on the server, and the data doesn't leave your, probably for you that's not so important, but for government agencies that last point is probably the most important. So I'll talk about the three things: the language, the data model, and the publishing framework, and then a little bit more about some future work. So does anyone recognize the character of Robert? Star Wars. Oh, you see, it's only our generation that these kids are all too young. It's Obi-Wan Kenobi. Star Wars, Master Jedi. So learning Obi will make you the Master Jedi of computational design. So Obi is the language, the name of the programming language, and we have an image of Obi-Wan Kenobi there, but it's only some of us who get it. All right. So Obi is in Mobius. Mobius, if you take the middle, is Obi. And so the programming language in Mobius is called Obi. And it's a new type of visual programming language. And I'll explain kind of why we did that. So when you look at all the computational design tools out there, they all kind of use the same approach of nodes flowing connected with wires. And the nodes are some kind of modeling function, and then the wires send the data to the next modeling function. By drawing these nodes and wires, you get this, spaghetti stuff that then you click go, it does something. In general, it's a nice approach because you can play around with the thing, it's very visual, and you can connect lots of different things together. The problem is that because every node is just one function, you end up with a lot of nodes. So, since every node just does one little thing, to do anything complicated, you really need a lot of nodes. And so that is where that whole problem of spaghetti code comes in. You get hundreds and hundreds of nodes, and then usually, in the student presentations, they're very proud of this model. They print out their screen capture of this thing, and it's this huge mess. And from a computer science point of view, it's like the worst possible thing, right? You don't want to have complexity. You want to try and reduce complexity and keep it as simple and understandable as possible. The other problem with these networks is that it's very difficult to do loops. So looping is a construct in a computational system where you say, I want to repeat something 100 times. So usually in a computer program, you write a for loop. So you say from I equals 1 to I equals 100, I'm going to do this over and over again and repeat it. In these kind of flow diagrams, the data just flows in one direction. It starts somewhere and it ends somewhere. And it kind of flows in a very kind of linear way. So it's very difficult to do loops. So Grasshopper has a plugin, whose name I've forgotten, that does some loops, but that becomes also very complicated to use. Houdini has loops inside it, but it's also not that intuitive to use. So looping in general is very difficult. So, so when you look at those kinds of tools and those parametric modeling tools and compare it to BIM and those kinds of tools, there are different types of parametric modeling. So, there's more than everybody says their tool is parametric, but actually some are less parametric than others. So even SketchUp, has some things that you can change, but it's not really parametric in the iterative sense. But I mean, you can have SketchUp objects where you have a parameter and you can change the parameter and the object will change. So that's what we call object-based parametric object modeling. Then the second one is associative modeling, which is actually all the CAD systems, and 3D Studio has this kind of thing inside it, and Inventor, Autodesk Inventor. they have this kind of where you can associate one piece of geometry with another piece of geometry, so that when you move one thing, the other thing changes, or when you, it's basically association between geometric objects. And with those associations, one of the things that this iteration is to do with the loop. You can only kind of do one operation in the loop. You can sort of say, okay, I'm going to extrude everything, so it'll loop through all the things and extrude them. But you can't say, I'm going to extrude and cut and do three things. You only do one. Then with data flow modeling, like in Grasshopper, you can do iteration, but it's implicit in the way you structure your data. So, who's done Grasshopper here? No? You guys. So Grasshopper, I think there's some workshops. I think the workshops are for. Do you need that? I think the workshops are for SD. But anyway, there's some workshops coming for Grasshopper. But I think the Grasshopper approach is quite limited in how you can do iteration. And then the fourth one is procedural modeling, where you really have explicit looping and all that kind of stuff. So OB is combines the last two. All right, so this is the aim of OB is to say, okay, the image missing at the moment. There's an image missing in the middle there. So this was an example where we compared Grasshopper to OB. And so on the left side, these are models that are creating kind of spiral form, some kind of spiral form. Not so complex, a little bit complicated with different spiraling. That's the missing image, is the spiral form. So the models on the left are creating the spiral form using Grasshopper, and the model on the right is the same spiral form using Mobius. So really this is the aim, is to try and reduce all this complexity down into something which is more similar to a flowchart that you learned in high school. Like a kind of, you know, a very simple flowchart where you have a bunch of boxes and each box does something. And it's, as much as possible, we try and make it sort of quite linear and there's not a lot of wires and all this kind of stuff. So the way we do that is that inside each one of these little boxes is a little script, a little procedure that you write. And this procedure is like a programming procedure that you would write in Python or something. But in this one, it's like a drag and drop thing. You insert the function and you fill in the blanks and then it will do something. So, so if we look at this, so each one of these bars here is a line of code. And when you're executing a procedure, basically the computer starts at the top and goes one line by line, and does each line. Like it does the first line and then does the second line. And so this everything variable here is the name of the variable, and then this is the name of the function, and this is the input to the function. And this collection here is the next variable name, and this is the function, and these are the inputs to the function. So it basically means that, let's say with this query.get, this gets some geometry from the model. So the collection will be is equal to get all these collections from the model where something named blocks. So you're kind of getting something there, and then here we're saying this collection here goes back here, and now you're saying get from this collection some plots. And then here we have the loop. So you say for each plot in plots, so you're going to repeat something for each plot. So basically these extruded buildings are here. You're repeating for each plot, and then plot you're extruding the building. So for each plot, you're going to calculate the area, and if the area is bigger than 1,000, then create a random number between 3 and 30, and then extrude them. So, who's done any scripting on school or anyone? I think the new, yes, good. So the new curriculum, I think is becoming more and more common. I think maybe you missed that part. So, but the scripting is so really part of the Mobius challenges is learning this scripting. And so we found that we've been teaching this in US, and some people really struggle a lot with it, and some people kind of get the concept quite quickly. And the scripting is not so difficult. You just need to really think in very simple terms. So you really need to think every step of what is happening and how you're going to do it. So here in this case, it's very simple. I mean, it's only 10 lines long, but it's still quite it does quite a lot in 10 lines. If you did this with nodes, you'd have like 10 nodes, and then it would already be quite complicated. In this case, in this example here, the generate buildings is extruding the buildings. The top line there, import data, is importing the base model of all the geometry. All right. So here is the plots of buildings. So one of the things that OB has is this query language. So there's this model that you're always talking to this model. You're adding geometry to the model, or you're looking for geometry in the model. So when you do the query, you're basically looking for some geometry. You say, in my model, get me some geometry. And so here we can say, get me all the geometry that is in collections. The collections are these things here. So this is a drop down where you say, I want to get the geometry from the collection. And the collection must have a name equal to blocks. So all these polygons are in a collection, and the name equals to blocks. Then, so the query language just allows you to take things out of the model. So let's say you want to extrude. Now I've got to be careful I don't laser you. All right, extrude. You need to be, you take these polygons and then you extrude them. So the query is just getting the polygons, and then the second step would be extruding. So this flowchart then, when you look at this flowchart from start to end, you can also take the flowchart and turn it into your own function. So you can say, okay, I made some complicated flowchart to make windows. Then I can save my flowchart as a window function. And then when I make my building, I can say, okay, now I'm going to make windows with my window function. So you can make your own functions. So let's say in a normal CAD system, you have a function to draw a polygon, and you have a function to draw a line, but you may not have a function to draw a window. If it's a bin tool, you would, but let's say it's a model you make, and there's no tool for it, then you can make your own tool. You can make your own flowchart that does it, save the flowchart as a function, and then add it to motion. All right, so then the data format. So one of the things about the data is that when you look at BIM and parametric modeling, there's the key difference is that the parametric modeling is mostly geometric, and there's no semantics. So when you're doing parametric modeling, you're working with polygons and polylines and extruding stuff, but what you're getting is just geometry. You're just getting geometric entities. And you can have some, let's say, grasshopper, you can have some groups, and you can have some layers, and you can have some data. But all that stuff is not really attached to your geometry. Your geometry is just kind of meaningless geometry. And the only person who knows what it means is you, as a human being. Your computer doesn't know what it means, it's just a polygon. So the way that you can add semantics to your model is to add attributes. So attributes are these things here, and you have them a lot in GIS, but not so much in architecture. But basically an attribute, it says, okay, well, here we have this polygon here, and this polygon has a table here of polygon attributes. And it just says, polygon number 1, let's say, is a park. So here somewhere in this table you have, say, polygon 1, and then here you say, park. And then polygon 2 is something else, beach, and polygon 3 is something else. So you just add attributes to your geometry. You just add little labels to your geometry. And you can add labels to the points, or to the polylines, and the polygons. So by adding these labels, allows you to add semantics. The other aspect that we wanted to include in this data model is that we can add attributes not just to the polygon. So when you look at a polygon like this, this is the polygon, but it actually has a number of edges. 1, 2, 3, 4, 5, 6 edges around the polygon. And each edge has vertices. Each edge has 2 vertices. But in total, 6 vertices. So when you look at a polygon like this, and you look at the bits inside the polygon with the edges and the vertices, this is called the topology of the polygon. The polygon has some internal topology inside it. And this topology is very useful because we want to be able to add semantics and attributes to all these things. So when we have this polygon, we want to say, okay, this edge here, let's say this is your building site. And you can say this edge here is next to the highway. So if we're going to generate a building on here, maybe this is where the entrance is from, or this is where most of the noise is coming from. So you can add attributes to your model to say what all these things, to add information to all these things. And you can do that in 2D or in 3D. So in 3D you have the faces, you have a face and an edge and a vertex. In 2D you just have edges and vertices. All right. So the attributes, the topology, those two then get combined. Attributes and topology get combined in this new data structure that we use in Mobius called GeoInfo. So it's geometry and information together. And so the data model is something like this. You have a collection of objects. So objects are points, polylines, polygons. So these are the 3 types, and each one of these types of objects has some topology inside it. So you have the objects, you can put, like, if you have 10 polygons and they're all belong to one building, you can make a collection. Say the collection is my building collection. So the building collection contain polygons, and then the polygons will contain topology. And at the bottom here you have the positions, which are the 3D, X, Y, Z. So, and this, when you create that kind of structure, this is what it kind of looks like. You have a polygon, and then the polygon has a face, and the face is wires, and actually it kind of breaks down all the way to the X, Y, Z coordinates at the bottom. The PS positions are X, Y, Z coordinates. I won't go into that one. Okay, so the third aspect of Mobius, which is a little bit different from other tools, is this ability to publish. So you can convert any model into an interactive sort of web page. So really the idea with Mobius is that you, as much as possible, you try and get people to open up this kind of modeling process to a much wider audience. So with a typical tool, you're the only one who's going to be using the tool, and you're just doing your design, and you generate your design, and then print the panels, and then it's done. But there are a lot of other kinds of processes, maybe not so much for this BIM competition, but there are many other situations where you want other people to interact with your model. So maybe you want your clients to interact with your model and say, look, I've made this model, and go to this website and look at this, change the sliders and look at the options, and the client can explore some options and then gives you some feedback. Or you want the next level down is your boss. Usually your boss has no idea about computational design. So your boss will be a bit like the citizen, completely incapable of doing any parametric modeling. But so you can say to your boss, just don't worry, just go to this website and then you can test out my options and you can tell me which one I should develop in more detail. Or the next kind of more general level is that you can say, I want to expose it to citizens. So I've got a proposal for a development in the city somewhere, and I want different citizens to give their feedback on the proposal, and there are some sliders that they can change the building height or setbacks, something about the design. And the citizens can change stuff, and they can vote on the design, and they can say, they can change it and submit their preferred options. So there are all sorts of ways that publishing is actually could be a very useful approach. So maybe not so much in this project, but I thought I would include it anyway, just to give you a sense of why we're doing it. So this was a Beijing workshop we did in Beijing last year. And we had a kind of 5-day workshop where 16 students came along, and none of them knew any programming. So in day 1 we learned the Mobius programming. In day 2 we learned about the data side. In day 3 we started developing some models and developing narratives. In day 4 we did some online searching of geospatial data, and day 5 was publishing models. So these models were not building models, but they were more data visualization models. Models for visualizing different types of data about different places. So this data here is the population density versus the distance to MRT station in Singapore. So the distance in which color is distance to MRT? So when you see the red ones which are tall, they are the ones, I think when you look at certain red ones here which are tall, there are clusters of residential that are far from the MRT. But mostly in Singapore you can see the density follows the MRT. But so this just allows you to start exploring this kind of data. All right. So the students did different kinds of models. So this one is of Tokyo, looking at population density and price. In the center of Tokyo, the price gets so expensive that it goes down. And so these models are then like a web page where you can just go to the web page and read the description and change some sliders and visualize the data. And this one was more recently. We also did it so that you can embed the Mobius model inside the web page. So here, these are 2 different versions of the model, are 2 inside one web page, or this one is just embedded in a web page. So you can have a web page with some text and stuff, and then just embed your Mobius model inside it. This is just done using Google Sites. So this is all free technology. Everything we show you here is free. Very important. And this is another example. This building here is one I'll kind of demo later on. So this is just a website, again describing something about building, and then you have a little viewer inside the website. All right, so the Mobius modeler then. So those are the kind of 3 key ingredients of the Mobius model, let's say. So if we look at the Mobius modeler kind of approach, it's really that, well, there's this Mobius core platform, which is the main platform. And on top of the platform, we have different applications. So the one I was just showing you from the geospatial, from the Beijing workshop, is a geospatial version of Mobius, looking at geospatial data. And then the one I'm going to be talking about today is the parametric modeling one, which is for parametric modeling. So on the platform, there are different kinds of apps that have been developed. And with each app, you can then publish different models. So from, this is the core, and then this is this app, and with this app, you can publish these models. With this app, publish those models, and there'll be more in the future. So it's like a kind of stacking up on top of each other. Behind the scenes, if you look a little bit more detailed, there's a whole bunch of stuff going on. I won't really go into this in much detail, but just to say that on the left side is basically what I've been talking about. The core platform has a language inside it and has the web application. And then this is the Mobius parametric model is the one we're going to be looking at later, which has the geo into a data model, a modeling library, a CAD viewer, and a geo viewer. So this is like the thing that's built on top of that, and then here you have the published model. And then the edX part is, I'll mention that later again, but in October there's going to be an edX MOOC. A MOOC is a massive open online course which is a course that you can do to learn Mobius. So it's a course which is online and you can have 10,000 students at the same time. And so for this course, we're developing also some stuff which is running on Amazon. So you can do your assignments and you submit it, and then it will automatically be graded. So, but if you want to do the course, you can come back in October. 1st of October it starts. All right, and so yeah, the different, Mobius model has been developed for a little while now, since about 2015. The first version came out in 2015, and has been, as we've been testing it with different people and teaching with it, we keep trying to improve it. And mainly the improvements we have made is kind of the reverse of what usually happens. The first one here was the one with the most features. It had very advanced features. You do a lot of stuff, and every time we're trying to simplify it and reduce features, take stuff out and take stuff away, and make it simpler and simpler. Because we realize that the complexity also gets very big when you have too many possibilities. So each time we're trying to look at how to reduce the complexity. So now the final, this graph here was more complicated. You could have different nodes with multiple inputs and outputs. Now we have a very, very simple graph structure, this flowchart, where you just have a box, and it always has only one input and one output, I mean it's just one arrow, and there's only one model coming in and one model going out. So it's a very simplified flow. Whereas this, I mean, if you look at this diagram here, you can't really see so well, but it was too complicated. It's a lot of wires, a lot of complexity. So we keep trying to make it simpler by removing stuff. So basically, the workflow is always you start with the flowchart. You structurally you think about, okay, what am I trying to do, and you break it down into a flowchart. You say, I need to generate this model, so I'm going to start with this bunch of 2D polygons called plots, and then maybe the next node I will copy the plots and extrude them, and then the next one I'll make the facade, and then the next one I'll put a roof on top. So you break it down into some logical steps, but those steps can be empty. You just structure it like a flowchart. And then you go inside each one of those boxes and start filling in the code, where you say, okay, whatever I said I was going to do, now I've got to do it. So then you've got to write a few lines of code to try and actually do that step. And then the third part is, visualizing it. So you can then visualize it. So when you look at the interface here, code is on the left. There's an execute button, which I can't see now, somewhere up here. And the 3D model's on the right, and then the attributes are down here. So these attributes are attached to this geometry. So let's say this one here, we can see that there's the collection here has an attribute called name, and the collection 0 has the name is blocks, and the collection 1 the name is blocks excluded, and collection 2 is canals. So these are just attributes that we have. The modeler, you just add some data to your model. They're just labels. You can add whatever you want. You can add data to your model, and that data then becomes very important in your parametric modeling. All right, so we'll look at the demo in a minute, but some future work. So in the demo, we will see that we have created an exporter to go from Mobius to SketchUp, well, to Collada. So from Mobius, you can export and then import into Collada, or you can import into ArchiCAD or Revit. Actually, it's only been tested with ArchiCAD, so I'm not sure exactly how it works with Revit, but I think you can also import Collada into Revit. But so the workflow then is that you get the geometry in as a kind of simple kind of massing, and then you need to convert the massing into BIM objects. And that's a little bit it's possible, but it's a little bit limiting. So one of the things we will be doing in the future is also be able to export to IFC. So IFC is a BIM modeling standard. And so if we export as IFC, then we will be able to get actual BIM objects in the BIM software. So that is still coming. The other part is the GIS part, which we're working on the same thing with GIS to integrate Mobius into ArcGIS. And probably you guys are not really using GIS, but it's another very important part of computational design is using geospatial systems. And the MOOC, so we are doing we're learning a lot of stuff for the MOOC. So the MOOC is going to be all lots of videos and stuff. So if you don't manage to learn Mobius for this in this current competition, then the MOOC will be very easy way to learn Mobius because there will all be videos and interactive tutorials and so that. And Mobius Optimization is really creating parametric models, then uploading to the cloud, and then using cloud computing to do the optimization process. So the first image I showed you with all those different point blocks all arranged, this is actually each one of these points, these are two performance criteria on the two axes. Each point is a different design. So each point represents a whole 3D model. And then you can evaluate the models and you can say, well, the best ones are sort of in this direction. And so you can look at these designs and pick them and have a look at them. Whereas these ones are all designs that got kind of rejected in the process. So that is another future development. And now we're going to switch over to demonstration. So for the demonstration, I will focus on this example that we did for the students at the US. And I will just go through, I mean, in this session you're not going to be able to learn. I can't unfortunately teach you programming in half an hour. But I'll just give you a little bit of a flavor of it. And then you can sort of get a feeling for whether it's something you would be interested in. And so I'm going to look at this particular model here, and then we can import into SketchUp or into ArchiCAD. And we will look at some of the issues that come. So one of the issues that comes, this one that works fine. I mean, SketchUp is just a geometric model, so it's not an issue. When you are importing into ArchiCAD, you're going from you're importing a Collada, this Collada file. Collada is one of the 3D file formats. Then when it comes into ArchiCAD, it's not a BIM model, it's actually a geometry model. And you need to somehow convert it into BIM. And some of those processes are tricky, and I'll give you an example of one that we're still on our to-do list where we are trying to, we have some slabs, and when ArchiCAD imports it, they don't become solid, they stay as kind of shells. So there are kind of issues. I think when you're working on this BIM competition, these kind of issues when you import something and it doesn't come in exactly as you expect are to be expected. I think students sometimes think that because there's all this software, it will just work. Well, in general, you should expect it not to work. You'll be happier at the end. If you expect it not to work, and then you do something and it works, you feel so good. Right? If you do it the other way, you expect it to work and then it doesn't work, you feel very sad. So it's better to expect it not to work. Because 50% of the time, not to do with Mobius, but with any kind of BIM, going from Grasshopper to BIM, or going from geometric modeling to BIM, and all these workflows are very tricky. The data models are very complex. There's a lot of stuff going on in the background, and very often things don't work. And that is why VCA creates this competition to try and get people to engage with this and struggle and figure out what works and what doesn't work. It isn't just kind of just click and it will work. It takes a lot more pain and dedication and sweat, blood and tears to get there. All right. Let me see how am I doing for time. Do I have half an hour? About half an hour? Yeah. Hey, my NUS student. No longer student. way, but I think with the microphone it should be all right, right? So, let's have a look at some of this stuff. Okay, great. All right, where do we want to go? We want to go to I mean, are there any questions before I go to this bit? Yeah. All right, so when you look at Mobius, when you first arrive, there's these tabs along the top here. Move this up a bit. Now, I need to switch on my internet. So the tabs at the top here, the first tab gives you just a little kind of introduction to Mobius, and it has some links at the bottom here which are quite handy. There's a book, a Mobius book, which explains a lot of the concepts behind Mobius and has some help and stuff. So if you're trying to figure it out on your own, do look at the book. There's the forum. So the forum, you can see all the students from NUS struggling with Mobius. There are many questions on there. So you can go on the forum and have a look at the questions there, or if you're doing something, you can also create an account and ask questions. And then one of us will answer it. What was the third one? The source code. So if you are so inclined, you can also contribute to the source code. It's all on GitHub, and but I'm presuming probably you are not going to be programmers at this stage yet, but still, all the source code is here on this code repository. And there's a link to the Design Automation Lab, which is the lab where we developed this, and you can have a look at the people here and the different projects that we've been working on. All right. Second tab is a gallery where we have some examples, some example models. So let's just look at this simple spiral model. So basically you have we look at these tabs. So if we look at the first tab is the tab with parameters. And in this model there are no parameters, so there's nothing here. But if you've got sliders and things, they will be visible in this tab here. The second tab is the flowchart. So it's basically like a flowchart as a start and an end. The start and the end can not be deleted, but this node is the node that contains the code. So if you want to create a new node, you can just double click and it creates a new node. Or if you want to go inside the node, you can double click that and go inside. So the flowchart, when you look at the model, if you click on the start node, your model will disappear because you just started, there's no model. And then when you click on this one, you'll see the model that is coming out of this node. A bit like most of the parametric model. And then when you click on the end, so you can have, in this model, it's just one node. I'll have a look in a minute with more than one node. But so basically it just goes from start to end. Double click on this, then you see the code in this model. So we can see here a very typical bit of code. We say we're going to make 20 steps in this staircase, and we're going to say from range 1 to 20. So actually it's 19 steps. Start with 1. And then we say we're going to make a rectangle, which this rectangle is actually just 4 points. And then this is the 4 points here, and then we say we make a polygon. So let's just we can just disable these ones. So we can click play, and then we can see, okay, now we're creating a rectangle and making a polygon. And polygons are just going straight up. So the rectangle is, this is the coordinates of the center of the rectangle. The rectangle's center point is at 35 units, which are meters. In this case, we assume they're meters. It's a very, very large staircase. It's not really supposed to be a staircase. It's just a general example. Looks a bit like a staircase. 35 meters in the x direction, 0 meters in the y direction, and I times 5 in the z direction. So I is this loop. So here you're looping through, and this is the I. I is first time around the loop, it's 1, and then it's 2, and then it's 3. So that is why this thing is going up. So each one of these polygons is 5 meters up. If I say I times 10, then they go up further. So it's a very simple kind of structure. And then this 50-10 is the size of the rectangle. 50 units by 10 units. So if I say 50 by 20, I'm going to get a bigger rectangle. So these functions here that are in here, they're just functions from a list of functions that are from here. So I can say, okay, polygon, let's say I want to extrude this polygon. I can go down here and say extrude. I say this is going to be extruded. I'm going to extrude my polygon. And I'm going to say extrude at a distance of 2, and I'm going to have 1 division, and it's going to create a polygon. So these are just functions that I can drop in. So they're just I just click them and then drop them in, so I don't need to type I don't need to remember the function and all that. I can click this little question mark here and get help on my function. And yes, that's that. So let's get rid of the extrusion for now. So each time I change something, I just click the play button, and then it will play the script. So it just plays the script whenever I change something. Click play. So then the next one is get the edges. So what I want to do, so let's just rotate this first. So here, these ones are disabled. So I go from making a polygon and then rotating it. And the rotation angle is this. So I don't know whether you remember your primary school maths. Do you remember that there was a thing called radians? Yes, right? Singapore maths, damn good. So radians this is pi, so the angles are measured in radians. So pi is equal to 180 degrees. So pi divided by 8 times I means that this is deciding the angle. So if we just say pi divided by 4 times I, then you get something else, right? Pi times 10. That. So the smaller dividing by a bigger number obviously makes it smaller, and give you a different shape. So, all right. So now, actually, what we want to do is to make the steps. If we're imagining these steps, we want to make this side a bit longer than this side. We kind of want to splay them out. So this is an example where the topology comes in quite useful. So if this is just a polygon and I want to make this side longer, it's actually quite a complicated operation. I'd have to, I don't know, find this edge and then maybe draw a new line there and then loft or something complicated. But now, because we've got topology, we can say, I want to have the edges of this polygon. So here we say, get me the edges of the polygon. So this query here is saying, I've got this, I just made a polygon in this line. And so in this line, I'm saying, query.get edges of this polygon. And this one is a condition, but we set it to null, there's no conditions. So this one returns, this is now the 4 edges. So we can print this. In programming, when you're programming, usually what you do is you print a lot. And print basically means that it prints a little text message. So it's a very normal kind of approach in programming. If you click play now and click this, then you can see this little print thing here. If I switch it off, there's nothing. If I switch it on, then it prints this message. So these are the 4 edges, edge 0, edge 1, edge 2, edge 3, edge 4, edge 5. So this printing here is just a way for you to check that your program is doing, your code is doing what you expect. So you often print stuff just to have a look at it and say, yeah, there's 4 edges. Otherwise you don't know that there's 4 edges. You can also, instead of printing, you can click this other button here, which is show geometric entities, and when I click that one, it will actually show me that there's 4 edges, 0, 1, 2, 3. So when I look at my edges here, I can see 0, 1, 2, 3, edge 0 is E72, edge 1 is E73, so I can actually see the edges, how they are numbered. So those are my edges. So actually what I want to do is this edge number 1 here, I want to make it longer, right? I want to make that edge longer so that this step gets wider at this end than it is at this end. So I can say, okay, I'm going to scale this edge, scale it up. So if I scale it up around the, if I scale it around the origin here of 0, 0, 0, the edge will also move. If I want to scale the edge and I want it to stay in the same place, just get longer, then I should make my scale factor, my scaling, have the origin right in the center of the edge. Right? You know, if I scale around the center of the edge, then the edge won't move because the center, you're just making it longer. So I first calculate the center here, so the centroid of the edge number 1, so that's edge number 1 there, that's the centroid. I print that, let's have a look. Our scale factor is, so there's the center of each of those edges. And then I scale. And here I'm scaling by 2.9, which might be, so it just scales up that side of it. So it's just a very simple example of kind of looking at the code, understanding, I mean already there's a for loop here, like the loops, there are always lots of loops. So usually you're doing something over and over again and looping through stuff. So we can do stuff like, let's say when we look at these polygons, if we go and look at the polygons, we can see here, these are the polygons that are in our model. There are 18 polygons, 0 to, well, 19 polygons, 0 to 19, 0 to 18. So those polygons have no data on them. We could add some data. We could say, okay, I'm going to add a bit of data to my polygon. Let's calculate the height, and we know that this is the height, right? That's the height of the polygon, I times 5. So let's say we're going to add a bit of data to this polygon. We're going to say my polygon attribute height is going to be I times this height here, I times 5. That's the height that we're setting. So now I've added a column here to my model. Now each polygon has actually some data attached to it. So each one of these polygons now has the height attached to it, has some data. So that could be that data could be something I want to use later in my parametric modeling or something. I can actually also say, type equals step. So I can say the type of polygon is a step. So now I've got a column that says step, and if I have other polygons that are handrail and stuff, I could say type equals handrail. But then I have a way of, it's kind of halfway between parametric modeling and BIM modeling. You're doing parametric modeling but with semantics, and you're attaching the semantics to the geometry. So let's say the edges here, edge 1 was the outer edge for our handrail, right? So we can say here for the edges, let's add an attribute to this edge as well. So let's say variable edge 1 attribute type equal outer. So this edge is not a polygon, so it doesn't appear here now. If you go to topology and edges, you see that there are some edges now that are the outer edge. This is this outer edge which we scale. So edge number 1 type is equal to outer, so these are outer. So now if I want to make a handrail on this staircase, I could say, get me all the outer edges. So query get outer edges. And I want to get all the edges where the attribute type is equal to outer. So this is basically saying, get me all the edges in the whole model, null means the whole model, where the type is equal to outer, because I created this outer type. That will get me a bunch of edges. So let's just print that, check that I've got some edges. Go here. Yes, I've got a bunch of edges. So let's extrude those edges to make a handrail. Extrude, query, make, extrude, outer edges. This is some kind of, the scale of this staircase is very weird, so just say it's 3 meters. All right. So this is an example where we're adding an attribute. So we added an attribute to the edge outer, and then here we're getting all the outer edges. So these attributes, this ability to add semantic information to the model, is a key part of the way that you do the parametric modeling. Because you add labels to stuff, and then later when you need to use that geometry, you just say, get me all the stuff with this label. And that's how you very easily manage the complexity of your model. So you don't need lots of wires, you don't need lots of complexity. You just add the labels in a way that, and it doesn't matter what label. I mean, if I could have called this something else, as long as I use the same name when I get it, as long as this name and that name are the same, then it'll produce the same result. So this kind of demonstrates the working with attributes in the model. And for architects, they're very, very focused on the 3D view. And I usually tell them, you should practice modeling like this. Because actually the data is more important than the geometry. You need to get your data right, and you need to put the attributes in the right place. And first look at your data. Most architects model like that. Right? So you need to, okay to have both open, but the data is very important. I'm looking at the time, I've only got 7 minutes left. All right, so the other thing is that every model is in some geospatial location. So there is automatically a globe in here, the whole planet, and everything you do, the default location is here in NUS because it's just across the road from you guys. So this is the default location, but you can place your model anywhere in a geospatial location, and you can import geospatial data from data.gov.sg. So you can import all sorts of data and embed it all that kind of stuff. Now, I want to show the building. So let's have a look at this more complicated model, which is the model that has some different floors and a bit more complicated structure. Just to give you an idea of how you would structure a more complicated model. So basically, you don't structure a model based on, let's say this has got 10 floors. You don't say, okay, I've got 10 floors, I'm going to have 10 nodes. In node 1, I'm going to do the first floor, node 2, the second floor. That is not the parametric way of thinking. The parametric way of thinking is that you structure it as a skeleton first. So you try and create a model where you start with a very simple skeleton of the whole thing, and then you add information. So we start with the base, which is just the base of the model. So the first node creates the base, and the second node creates a bunch of floors. So we don't want to immediately add handrails and all that stuff, because if you add too much information on this level, then in the nodes further down, you're just going to be struggling to ignore that information. Like if you've got handrails in the first node, then in the second node, you're going to have to do something where you don't want handrails, and then you have to try and delete the handrails and all that. So you want to keep it very simple at the top nodes and gradually get more complicated. So then you can say, okay, these are the floors. Now one thing about these floors, and so this is the interior floor. If you look at this little piece here, let's say you're standing here on in this building, the rain will fall on your head, right? Because there's no slab above you. Actually, no. If this is an interior floor, the slab above has to be bigger than this one. So the next node actually makes the slabs. So this node makes the interior floors, and then this one stretches the floors so that there's no holes anywhere. And this one then stretches the balconies, identifies the balconies which are in the model. So this is the floors, this is the slabs, and this is the balcony. Then the slabs in this one get thickened, so you get a slab thickness. And in this one is where we add the handrails to the balconies, so that at the end you get, these are basically the balconies here, and the handrails are those bits, balconies are those bits, and the slabs are those bits. So the slabs and the handrail, this part sits on top of the slab. So let's say over here there's a balcony. Yeah. On the other side, so one side you're doing kind of the slabs and the balconies. On the other side of the float, you're doing the facade. So here we extrude the floors into facades, just polygons. Again, you keep the nodes so that it's simple at the beginning and gradually gets more complicated. Then you do a I've forgotten what we did there. So we don't want to have windows on these facades, right? So we don't want to have windows here, we just want to have windows on this side. So the next thing is to add an attribute that categorizes polygons into the direction they're facing. So here, if we look at the facades here, we just have polygons, and they've got a type called wall. And then the next node here says set orientation, and it says orientation, you can say south-facing, east-west, south, east-west. So you can set the orientation. My spelling mistake there, east-west, east-west. So that sets the orientation, and then you can say in the Windows node, you can say I only want windows for certain nodes, not all orientations, only for certain orientations. In the end, that all comes together in this model here. So this, the stepping in and out is actually created using a randomized function. So each time you run your script, you will get a slightly different
then the third one here just adds some glass materials and things like that, so you get some glass materials. So if we then import that into, I mean, that just imports into SketchUp as a SketchUp model. So we can do, the thing I kept cancelling is the last node here. I have, yes, final node here, I have export data as DAE. So DAE is the collada file format. You can choose some different, GeoJSON is a geospatial format. DAE, OBJ, and GI is our own geoinformation model. So this is our own file format. And these are the other ones which you can import. So DAE is the SketchUp format. But we can import it into SketchUp and ArchiCAD. And so whenever we execute this, this is why when I execute this thing, it comes up and tries to save this file. But I already did it, so I can cancel it. So I can either disable this and then it will stop asking me that question all the time. And then we can look at that. So in SketchUp, it basically comes in like this. We can explode this, and it becomes just a normal SketchUp model that you can then do your usual SketchUp modeling on. So the idea is that you don't have to model everything in Mobius. You do your basic, you might do certain kinds of modeling in Mobius and then bring it into other packages and edit it. And in ArchiCAD, this one. So let me just do this one. So when you bring it into ArchiCAD, there's a few more steps. So let's just try that. I think I've got about I'm at -1 minute. All right, do it quickly. I can't remember now if that was the right one. So how many people have used ArchiCAD? No one? Some over there. So let's have a look if I've got the right one. Yes. So oh no, this is not the right one. Bring in the full one. I think it's that one. So by default, it comes in as this imported object. So you can select this object and convert to morphs. It says this is a very big object, but it's not that big. And when you import it in ArchiCAD, it automatically triangulates all this. But you can just select the object and get rid of the triangles by clicking this hidden thing here. That will get rid of the triangle, so you get a pretty clean model. Now, the model here would require, so we've run out of time a bit, but the model here would require some additional steps to actually turn it. I mean, you can already cut a section through it and that kind of thing. So you could already use the model as it is. But to turn, let's say you want to turn these slabs into actual BIM objects, then you need to do some additional steps to make the slab actually a BIM slab and assign concrete to it and stuff like that. So there would be some additional processes to turn this into BIM objects. And that is why also we are planning for the IFC export so that we don't have those additional steps. Basically, we want it so that it should just come in, you immediately have a BIM model. All right, I think that's about as much as we got time for. Let's have a look at this. Go back here. Is there anything less? No, that's it. All right, thank you very much. So I think any Q&A?
How does the facade know the orientation? We
So for the orientation thing, you take the polygon and you measure the angle between north and the polygon's angle. And so if the angle is, I give it a range. So if it's between, you know, -10 and 10 degrees, then I say it's facing north. And if it's between 80 to 100 degrees, it's facing east. And so I give it kind of a range. But it's up to you as a modeler to set all these things and set them on chip. So you can do, you know, different styles of chip.
So the north is showing the...
North is by default the y-axis. North is y and then x. Yes? No? No question? So I think so hopefully I will see you on the forum. Right? So my usual, I think my response on the forum is less than an hour. Right? If you ask me a question, I can respond unless it's the middle of the night. So I try and be very responsive on the forum to get the community going and to get you know, people using Mobius and interested. So yeah, if you've got any questions, then you can email me, or you can go to the forum, or try stuff out. It's all, and so everything is available. And so over the next few months, we are going to be doing a lot of work in preparation for the MOOC. So there's going to be a lot of videos, and we're going to improve the book, and we're going to do tutorials and things. So also, the health information is going to get a lot of love and care over the next few months. So maybe I'll see you in the room. All right.
Okay, the video will be posted in YouTube, but I will email the